If we could, we would build this thing called a sampling distribution. And the sampling distribution is the distribution of the sample statistic under repeated sampling from the population. So if all of your samples are randomly selected, the sampling distribution is going to be centered around your population parameter. So, for example, if we were making a sampling distribution about means, we would have many different data points in here that would all be different X bars, different samples, but the distribution would be centered around mu, the true mean. Similarly, if we were doing this about a proportion, we would have many different p-hats, different proportions from our sample, but the distribution would be centered around p, the true proportion. So this is kind of magical because it means that if we were able to go do some repeated sampling, we would be able to figure out what that value of the true population parameter was. In addition to that, if you have a big enough sample size, your sampling distribution is going to be symmetric and bell-shaped. So that's what I've been trying to draw here. Just a word of caution, if the samples are randomly selected, then the sampling distribution is going to be centered in that nice way. But if the samples are biased, the sampling distribution won't necessarily be centered there, and all sorts of things could go wrong in your analysis. So this is why statisticians really like those random samples. Okay, so we've talked about the center of the sampling distribution. It's centered at the population parameter. We've talked about the shape of the sampling distribution, roughly bell-shaped. And then the thing that we actually really care about is the spread of the sampling distribution. So we want that variability, and this is the thing that's going to allow us to answer the question, what are some other reasonable values we could have observed? So the variability of the sample statistic is so important that we've given it its own name. And this is another one of those cases where statisticians should not be allowed to name things. What they have named the standard deviation of the sampling distribution is the standard error. So the standard deviation is a general term, but if you take the standard deviation of a sampling distribution, it gets called this specific term, the standard error. So this is one of those things that I think is nice to have written down on a summary note sheet somewhere because it's easy to get those two terms confused because they both have the word standard in them and they're both essentially the same thing. One is just a more specific version of the other one. The standard error is going to measure how much your statistics vary from sample to sample. So let's look at a sampling distribution. I have displayed it to you as a dot plot here, but we could imagine it kind of smoothed out in a density plot like that. And each of these dots now represents a particular sample statistic. So let's say we're thinking about the mean. So this would be the mean from one sample, another sample, another sample. Sometimes we saw means that were as big as this or as small as this, but most of the time they were kind of centered in this middle area. So the question is, we're saying what are some other values we could have reasonably observed? And are these values reasonable? So is 1.1 reasonable? So let's look for where 1.1 would be. I've got 1 and 2, so here's 1.5. Let's say that 1.1 is right here. And that looks like it's a pretty reasonable value that I could have observed. It's near the center of my distribution, so it would be pretty common. It's definitely inside that, kind of eyeballing the 95% rule. And I'd like you to think about these other ones. So we said, yes, we could have reasonably observed 1.1. I'd like you to think about the rest of them, and we'll talk about that in synchronous class. And the last thing about sampling distributions is sample size matters. So if you have a larger sample, you are going to have sample statistics that are not going to vary as much. And the statistics are going to get closer and closer to the population parameter. So you can kind of think about this logically. If I was interested in the height of everyone in our class and I took samples of size 5, I might randomly pick 5 people who were really short and get a very small mean. Or I might randomly pick a bunch of people that are really tall and get a really large mean. But if I took a larger sample, if I took a sample of size 20 from the class, I'm less likely to get all really short people. I'm probably going to get a nice mix that's closer to the distribution of the population of the whole class. So as I take larger samples, the variability of my sample statistic decreases, and the statistics get closer and closer to the population parameter. So those are some facts about sampling distributions.